Hello students, in this video we are going to learn some basics about symmetry groups. What if I tell you that the symmetry group of this figure is isomorphic to D3? Will it be justified? Why? Now look at this. This is a triangle. Symmetry group of this figure forms D3. Now for rotation, what do we do? By which angle we have to rotate this figure? Which is 360 degree over 3. Why? Since this whole angle is 360 degree, which is equally divided into 3 parts. So for each rotation we have to rotate this figure by an angle 120 degree or 2 pi over 3. Right. Now let's come to the previous figure. This figure has 3 petals, this, and this. If you draw the vertex of a triangle at the tip of this petals, each petals, then you can easily draw a triangle. Right. Now see, there are rotations by an angle 120 degree as we have discussed in the case of the triangle. Right, this is 120 degree, this is 120 degree, and so is this. If we move this petal by 120 degree, this petal goes to the position of this one. And if we move by twice 120 degree, this petal goes to the position of this. So we have found 3 rotations. One is this figure itself, second is when this petal goes to the position of this one, and third is when this petal goes to the position of this one. So there are 3 rotations. Now consider how many reflections are there. See, there are 3 axes possible, about which this figure can be reflected. That means we can have symmetries if we reflect this figure about these 3 axes, right? So visually we can conclude that the symmetry group of this figure is isomorphic to D3. Now let us consider another figures. Take this one. This is somewhat similar to a pentagon. So we can easily show that this figure, the symmetry group of this figure is isomorphic to a pentagon, that is isomorphic to D5. And so is this. You can count the y's right here, and let us say that number of y is n. So this figure, symmetry group of this figure will be isomorphic to Dn. Well, all other can be shown to be isomorphic to some Dn. Okay, but what about this one? Is this isomorphic to D2 or D3 or D4 or something else? No. So what about the symmetry group of this figure? If we rotate it by an angle 90 degree, what does it become? It is not an S anymore, so it is not a symmetry. What about if we rotate this figure by an angle 180 degree? Yes, it will be another S. See, if we rotate this, it will be another S. So this can form a symmetry. Is there any reflection possible for this figure? No, there is no reflection possible. You can take reflection about this axis, say this one or this one, but this will not form a symmetry, right? So there are only 2 possible rotations or only 2 possible elements in the symmetry group of this. Next we will discuss how to write these symmetries in terms of permutations. And then we will discuss about some figures which are not in general discussed. And in the end, there will be an interesting fact for you. So now, you can see if you perform a reflection about this axis, this 1 goes to the place of 4, 2 goes to the place of 3. And 3 goes to the place of 2 and 4 goes to the place of 1. So how does these form a permutation? let us write the initial positions 1, 2, 3, 4. These are initial positions, and 1 goes to the place of 4 after this reflection. So we will write 1 goes to the place of 4 and 4 goes to the place of 1. These are initial positions and these are final positions. 2 goes to the place of 3 and 3 goes to 2. Okay, so these can be written as 1, 4 and 2, 3. Product of 2 cycles. Okay, now how do you write identity permutation or the symmetry itself, the figure itself? It will be written as 1, 2, 3, 4. The figure itself can be written as the identity permutation, this. Now you can see a reflection can always be written as a product of 2 cycles. But this is not really true for rotations. Like what? If you perform the rotation anti-clockwise in this anti-clockwise like this, then 1 goes to the place of 2, and the rotation is performed by an angle pi by 2, since this is a square. So 1 goes to the place of 2, 1 goes to the place of 2, 2 goes to 3, 3 goes to 4 and 4 goes to 1. So this will become what? A cycle 1, 2, 3, 4. So it is that simple. Okay, now let us consider the case for rectangle and not a square. Well, for rectangle, the case is a little different from square. How? You can see there are two reflections about the axis this and the axis this. These two reflections are similar to the square. Like 1 goes to the 4, 2 goes to 3, and this will become similar to this. Okay, but which type of reflection is not possible for a rectangle that was previously possible? You can see this the reflection about this diagonal is not possible for a rectangle. It was possible for a square because it was symmetric about this diagonal, but this is not the case for the rectangle, right? So it will not be a symmetry. Also, for symmetry of this rectangle, the angle by which you have to rotate to get a rotation is 180 degree. Okay, so 1 goes to the place of 3 and 2 goes to the place of 4. So it will become 1 goes to the place of 3 and 3 goes to the place of 1 as well, and 2 goes to the place of 4 and 4 goes to 2. So this is a product of 2 cycles, but it is not a reflection. This is rotation. And take a note, the symmetries of this rectangle forms a symmetry group which is called D2, right? For this one, this forms a symmetry group called D4, but for this one it forms D2. So well understood. Now let's go to a different figure. This is an infinite strip. Infinite strip means it goes to the infinity and it is never ending, right? Then can you find how many reflections or rotations are there? Are they finite? And there arises one more question. Is the symmetry group or dihedral group finite always? Let us find out. We can find a reflection about this axis. Well, we can find a reflection about this axis as well, and this, and so on. So there are infinitely many reflections. But how many rotations are there? See, you can take an axis like this and you can find only 2 rotations. One is itself and the other one is 180 degree rotation. See, 180 degree rotation. But when we fix this, like when we fix this axis from it is a 3D figure. Okay, this is the axis. When we rotate about this axis, it will become a rotation and form a symmetry. Similar, if we take an axis like this, and similar if we take an axis like this and so on. So there are not only 2 rotations, there are infinitely many rotational axes. So there are infinitely many rotations as well. Now, can you say, let us take another figure, which is a circle. What do you say about this circle? What do you say about this circle? How many reflections or rotations are there? See? And also, by what angle you have to rotate this? Let us say you rotate this by an angle theta. Okay, by an angle theta. You can always find a symmetry if you rotate this by an angle theta by 2. See, if you rotate this by an angle theta by 2, you can always find a rotation. So there are infinitely many rotations about by infinitely many angles, right? And same for the reflections. You can find infinitely many reflective axes, right? So this is also an infinite symmetry group, right? Now we have reached the phase where I'm going to tell you the interesting fact, which is, if you take this, a 3D body, like this, then the rotation and reflection are quite like the same. See, if you take a reflection, or you can say rotation, whatever, about this axis, joining this point and this point, okay, it will be a rotation. Also, if you take a rotation or reflection, joining these diagonal, okay, joining these 2 points, that forms a diagonal, and this is not a reflection, this is again a rotation. Rotate it once, rotate it twice, and rotate it thrice. It will become the previous one, and it comes to the initial stage, right? So about each diagonal you can rotate it thrice to reach the identity element. And there is the end of the video. Okay, thank you for watching, and don't